Okay, I'm going to go over a couple things with the lesson notes for inverse trigonometric functions and differentiation. This is a kind of a second look at some things. And I'm going to follow the bouncing ball here, if you will. So remember, when you deal with inverses, that you have a different setup where you have the sine inverse of 1/2 is equal to pi over 6. You're saying the angle whose sine is 1/2 is pi over 6. So we want to develop the properties of the 6 trigonometric functions, differentiate inverse trigonometric functions, and then review basic differentiation rules for elementary functions. And so we start off with this first problem. Now, this is going to be a review of how you handle the setup. So notice that if I have the secant of arc tan, I can let arc tan be equal to theta because it is an angle, the tan inverse or arc tan of -3/5. So once I let that theta equal arc tan -3/5, I can rewrite that then as tan theta before I begin and say tan theta is then equal to -3/5. And then I could set the ratio y over x equal to 3/5 and -3/5. And then I could solve for r by using the Pythagorean theorem. You see that I've drawn the triangle here. And so x is 5, y is -3, and then r turns out to be square root of 34. Now, the principal region for tangent is then from -pi/2 to pi/2. If you look at the graph of tangent, you see those two vertical asymptotes on either side of the y-axis. And that is the principal region for the angles for the tangent. So first, then I come back over to here and I say, okay, well, I want the secant of theta. I've set up the situation over here. So I've got the secant is r over x. And so I take the r, which is square root of 34, and I put it over the x, which is 5. And I'm able to say that the secant of the angle whose tangent is -3/5 turns out to be square root of 34 over 5 then. Okay, and then in the second example, we kind of do a similar thing, and we write the expression in algebraic form. Now, your x's and y can vary, of course, or your x's can vary here, but I'm interested in setting up the relationship if theta is set equal to arc sine of x minus 1. So I rewrite it as sine theta, and then remember, I was still working with the secant here. Secant theta is r over x. So what I'm going to do is come over to a triangle, set up the angle theta. So the sine theta is the opposite over the hypotenuse. And then again, I can use the Pythagorean theorem to find the adjacent side. So the adjacent side turns out to be the square root of 1 minus the quantity x minus 1 squared. It's also fine to leave it in that form just as is. It's not necessary that you multiply it through and then cancel the ones. It's actually a pretty nice form. Okay, and we get this. 1 over the square root of 1 minus the the quantity x minus 1 squared. Okay, all right, so again, there's another one, just working with inverse trig. So, and then you can take your graphs, and if you put in y1 is equal to tan arc cosine, that would be cosine inverse in this case, cosine inverse on your calculator, and put in x over 2. And then put in y2 as the square root of 4 minus x squared over x. You see that you get the same graph. One goes right on top of another. Keep in mind that the domain is only from -2 to 2. It's clear, and x is not equal to 0. Of course, you have that vertical asymptote. So both these, this is an and statement here. So it's actually -2 to 0, parenthesis 0 to 2. So then using algebra to verify that they are in fact equivalent, we'll take that tangent, here's the function, tangent of arc cosine of x over 2, and we'll let theta equal arc cosine of x over 2. Then we're going to rewrite it as the regular trig function, cosine theta is equal to x over 2. And then we're going to have tangent theta, recognizing that's going to be your opposite over adjacent, tangent theta. And we already started with cosine theta is equal to x over 2, so you see where we placed the x as the adjacent over the hypotenuse 2. And then we're going to take and say, what is that other side? So I made it a b using the Pythagorean theorem. We got b is equal to the square root of 4 minus x squared. And then we're able to say that our function, the tangent of theta, is then 4 minus x squared, the square root of that, over x. There you go. Okay, using the opposite over the adjacent. Okay, so katoa. And then identifying the asymptotes, that would, of course, be x is equal to 0. Okay? All right, and then we move on, solving equations with inverse trig functions. So sometimes it's helpful if we would say, if we rewrite it as the tangent function. So we could say the tangent of -1 is equal to 2x minus 5, just rewriting it in terms of the inverses. And then you can see that if you're going to solve this, it's helpful to solve for x then, because with that, then you could just say tangent of -1. You got to be careful with this, because this is the angle, if you will. So tangent of -1 is, and then plus 5, adding 5 to both sides, is equal to 2x. So we would then get 1/2 of tan of -1 plus 5, put parentheses around that, is equal to our x value. You should get an x value that is approximately 1.721. Okay, something of that nature. Okay, and always being mindful that you're looking at angles in, if we're looking at angles, if you're talking about an angle of -1, what does that look like? Then you can kind of reason that, we often throw numbers around, and you're looking at an angle that's in somewhere here, because if you come to pi over 2, if you go to negative pi over 2, then that's then approximately equal to 1.57 or something like that, right? 1.57. So in that case, an angle of -1 would be reasonable, okay? All right, and then we move on to the derivatives of the inverse trig functions. So what I'm going to do is I'm going to stop this. This is part 1, 3.3, part 2A, as we'll call it, okay? And then we'll pick up with the derivatives of inverse trig functions. So now you've already used these, so it shouldn't be too difficult to go back into this lesson. You could probably even do most of these on your own after the first lesson, but let's review some of these. Okay, I'll see you in a minute.